Okay, this is a quick video about non-uniform circular motion and beyond. And I say and beyond because if you understand non-uniform circular motion, you also understand all of 2D motion, polar coordinates, and fictitious forces. So I'll show you in this video how just understanding how circular motion works lets you understand all of those things as well. Just for a quick recap, uh, if you don't know anything about uniform circular motion, this video is going to be tough for you. So I do have another video that's on uniform circular motion. I recommend you go back and watch that. The key takeaways that we need from this are that in order to move in a circle, you must have inward acceleration. And if it turns out that your inward acceleration is this magic value, then the amount that your velocity changes by, so you go from a velocity that looks like this to a velocity that looks like this, the amount your velocity turns is equal to the amount that a circle of radius r turns, and thus you end up turning the same way that the circle turns. Okay, notice I put this in terms of this guy omega, which is your angular speed, and we're going to talk in those terms for this video. One thing that's going to be useful to talk about in this video is how acceleration changes velocity. So here I have this velocity vector and I have to turn it into another velocity vector later, and the acceleration is the guy that does that. In the case of uniform circular motion, this is a perpendicular acceleration, and basically you can think of the perpendicular acceleration as bending the velocity vector into that new vector. Okay, so this is not a concept just for circles. In regular 2D kinematics, you always have a velocity vector, and okay, you can find the components in the x direction, you can find the components in the y direction. That's nothing new. If we accelerate at some random direction, then the velocity vector changes by the way the acceleration vector tells it to. In other words, v initial equals v final plus a times t. Now, the same way that we can break the velocity vector into horizontal and perpendicular components, we do the exact same thing with the acceleration vector. In other words, that vector I drew earlier really has a piece that points along the direction of motion and a piece that points perpendicular to the direction of motion. What does the piece along the direction of motion do? It increases the size of the vector. In other words, acceleration along the direction of motion makes your speed larger. Of course it does. What does the one that's perpendicular to motion do? It changes your direction. It changes your direction. It bends you downward. Now here's a question. How do I know that a perpendicular also doesn't make it longer? Like, these two arrows look about the same size, but how do I know that in addition to bending it, it doesn't also make it longer? Well, there's a really easy trick in calculus that lets you figure this out. If you want to know how the size of something changes, that's d by dt, the rate of change in time of the size of that thing is actually the derivative of the dot product of it with itself. If you do that derivative, you end up with a dot v plus v dot a, and if a and v are perpendicular to each other, guess what? It's zero. That means that perpendicular accelerations cannot change your speed. They can't change the size of that vector. They can only change your direction. And that is actually very important and very useful. Let's relate this to circular motion. We want to do non-uniform circular motion, and the question is, what are the ways to make it non-uniform? One way is to change omega at fixed r. In other words, go faster and faster and faster and faster around the circle without changing our radius. And then there are these other ways as well. We're going to explore all three of them, and by the time we're done, we'll know how to do everything. Okay, so let's first look at this. Change omega at fixed r. That means that my tangential speed, this guy here, is going to have to increase. Another way to say that, though, is that my omega, which is my angular speed, so dot again means time derivative, that has to increase as well. So what does that look like? That means, first of all, I need to accelerate inward because I need to go in a circle, but I also need to make my speed bigger, so I need to accelerate in the parallel direction as well. So if I do that sometime later, I'll have a longer velocity arrow because I accelerated in the parallel direction, and later I'll have that same acceleration in the parallel direction. Now, if you look here, you'll see that I made the perpendicular acceleration bigger, and that is not by accident. The perpendicular acceleration has to get bigger. Why does it have to get bigger? Well, I increased the size of omega. If I increase the size of omega, the perpendicular acceleration also has to get larger. So if you want to speed up, you need to accelerate harder toward the center. So to recap this, for changing omega at fixed r, you have parallel acceleration. You tell me how much you want to change omega. That's how much acceleration you need. And then you have, as always, if you want to turn, you need perpendicular acceleration. And if you want to turn circularly, you need exactly that much perpendicular acceleration. Okay? We call this piece the tangential acceleration, and this piece is called the centripetal acceleration. Centripetal just means center seeking. Okay, so much for that. What's next? Let's see what happens when we change r at fixed omega. In other words, now, in addition to this tangential or circular velocity, I'm going to have some velocity in the r direction. I put a dot above the r, which means my value of r is changing. Out here, I'm at a bigger r. So what does that look like? If I move this way and this way, I'm going to follow this weird circular arc, which of course just leads to a circle with a bigger radius. Okay, but now let's think about this just a little bit. If I want to keep rotating that same rate I've been rotating before, if I go to a circle with a bigger radius, I'm going to need a bigger final speed. Why is that? If I've got a bigger final radius and I want to keep omega the same, I've got to have a bigger v tangential. If I want a bigger v tangential, guess what? That means that I need an acceleration in the parallel direction. I need an acceleration in the parallel direction. That's kind of surprising because my goal was just to move in the radial direction, but apparently in order to do that, I also need to accelerate in the parallel direction. So I have this piece, which is maybe a little surprising. This is the piece that we've had the whole time. We always still have centripetal acceleration. This is, I think, the most surprising thing. R does not change. I have a constant speed in the radial direction, and yet the direction of r changes. That's weird. That means that even though the speed in the radial direction doesn't change, because I change the direction, I actually need to change the velocity vector. And the change in the velocity vector has to look like that in order to make r change the angle that it sweeps at. So if that's the change in velocity, then of course the acceleration is d by dt, so that's r dot. And notice the amount that the radial vector has to bend is the same amount as the tangential velocity has to increase. And that's a remarkable coincidence, but it's not that I need one of those. I actually need both. So what does that mean? Merely by choosing to walk outward, if I choose to walk outward as I'm going in a circle, I am required to have a lot of acceleration in the circular direction. And of course, to go in a circle, I always need acceleration in the circular direction. This guy is still, as always, centripetal acceleration. This new term here has a name. It's called Coriolis acceleration. In other words, maybe you've heard of the Coriolis force and hurricanes and stuff. We'll talk about that later. It's really just the name for the part of the acceleration you need when your radius changes when you're moving in a circle. That is a mouthful, but we'll look at more of that in a minute. Okay, last way. First we looked at fixed r changing omega, then we looked at changing r fixed omega. Now let's change them both. Okay, what does that mean? Oh boy. That means that not only do I want to change the circle I'm going in, so I go from this circle to this circle, but I actually want to not just go as fast as I need to switch orbits, but actually go even faster on purpose because I want to increase the rate at which I'm accelerating. Okay, well, we can actually just assemble what we need from what we had before. Before, I know that in order to change my r vector, if I'm just moving at constant rate, I need to do that. But now I'm saying, you know what? In addition to that, I want the ability to change my speed in the r direction. So in other words, I'm including all the effects now. I can make the radial velocity grow and I can make it change direction. Likewise, in the tangential direction, I have, as always, I have centripetal acceleration. And now I've got two pieces here. One of them is omega dot. This term is responsible for me wanting to speed up my angular rate. In other words, I want to go around the circle faster. And the other piece, again, this is required because as we move to a larger orbit, we need a larger velocity just to keep up with the original omega that we had in the first place. So this is an awful lot of terms. So let's just summarize what we have so far. So I've got a radial velocity which changes, and that requires two different accelerations. And I've got a circular velocity which changes, and that also requires two accelerations in this direction and one acceleration in that direction. What I want to do now, we've made a bunch of arrows. Let's just do a little bit of calculus and see if math somehow can predict these answers. Okay, the first thing I want to do is exactly what I did in the uniform circular motion video. I'll just say that that is my position. My position is some radius, and whenever you're on a circle, the position, the x-coordinate goes like cosine theta, the y-coordinate goes like sine theta. If I want to know the velocity, well, okay, I take a derivative. If I take a derivative, I take the derivative of this, and I multiply it by the thing that was already there, so this becomes r dot. And then I take the derivative of this and multiply it by r. So here's r, and then the derivative of this whole term is the derivative of each term. And then remember, if theta is changing, I get chain rule, so a little theta dot pops out front. This is interesting already, because this tells us that the radial velocity points in this direction. This direction is the same as the radial direction because it looks just like this piece. In other words, this is that first term. It's this green arrow right there. How about this second term? This second term, if you plot it, actually points perpendicular to that first one. And that piece refers to the tangential velocity. So already the calculus has predicted that if I want to move both radially and tangentially, I end up with those two pieces. All right, now to find acceleration, you got to take another derivative. Okay, now admittedly, there are a lot of terms here. But one thing I want to observe before, you can pause and study them all. I just took another derivative, but I do want to observe something. There's this vector, and this vector. And then there's this vector and this vector. In other words, there's only two vectors here. So note that this last one is just minus the first one. But that means that there's really things only happening in two directions. And what I'm going to do is I'm going to invent a little bit of notation. I'm going to invent notation. That first vector, cosine theta, sine theta, I'm going to call r hat. The second vector, oh, shoot. Don't tell anyone I did this. I meant to write, this will have to be our secret, sine theta, cosine theta. Okay, that second vector, you get the idea. That second vector, I'm going to invent a name for, and I'm going to call it theta hat. Why? Because that second vector always points in the circular direction. And this first vector always points in the radial direction. So in some sense, look, we just invented polar coordinates. If I rewrite it this way, this is a very interesting way to write it, and I'm going to explain in 2 more slides where fictitious forces come from. Okay, so this says that in the radial direction, there are 2 ways to accelerate. In other words, to move in or out in the radial direction, accelerating in or out, there are 2 different terms. Likewise, there are 2 different terms for acceleration in the theta hat direction. What does that mean? That means that if one of them is non-zero, and you want the other one to be, and you want the entire term to be 0, then you need a non-zero other one as well. So let's just put names on all these things. They all have names. This r double dot, it's kind of makes sense. It's just the second derivative of the radius. In other words, it's the rate at which you accelerate inward or outward. This second term is the centripetal. That's the term that we kept popping up over and over again. In other words, what this says is if you have an omega squared and you don't want your radius to change, you are required to have an r double dot. That's why you will accelerate inward or outward when you're in circular motion unless you have an r double dot. Okay, and then this term, this is the famous Coriolis term. This is the thing that everyone finds weird, but I'll show you a video of it in just a moment. Okay, and then this guy's change in angular speed. So I think the first term and the last term are the most easy to understand. They are accelerating in the direction you plan to accelerate in, right? The other 2 are bizarre. So let me highlight this piece. And then I just want to show you a couple of videos. Okay, in this first video, I have a bead that is going to be pushed by this bar. And this bar, all it's going to do is rotate, which means it's always pushing the bead in the circular direction. It never pushes the bead in the radial direction. So let's see what happens. I start the video, and the thing starts to rotate. It's pushing it tangentially. And what is going on? Why did the bead move outward? Why did the bead move outward? The thing is that the bead isn't moving outward. The bead is trying to go in a straight line. But because we have omega, if there's nothing around to accelerate it, in other words, unless I have another piece, I'm going to have change in the r direction. In other words, I'm not pushing it inward or outward. Just by pushing it circumferentially, I cause it to move outward unless someone comes along and prevents that from happening. This is called the centrifugal force, and there is no force. It is just a piece of the acceleration term, and that's why they call it a fictitious force. Okay, so here's another one. This is for the second piece we have here. This guy is angular acceleration, and this guy is the Coriolis acceleration we were talking about before. So these two blue guys, the inner blue guy is just going to do normal circular motion. The outer blue guy, I swear I'm keeping the tangential speed the same. All I'm doing is telling it to move outward, and watch what happens. So it is moving outward, and I swear I'm keeping the tangential speed the same, but look at what's happening. It looks like it's slowing down. It is not slowing down. I swear it's not slowing down. But from the point of view of the light blue one, it actually looks like it might even be moving backwards. That is not because there is a force pushing it backwards. It's because there isn't a force pushing it forward. So this is the so-called famous Coriolis force. Coriolis forces make things look like they're moving in the tangential direction. So like if you take a ball and you're on the earth, and the earth is rotating in this direction, if you throw a ball straight up, you'd think the ball would just do this. But it doesn't. The ball does this weird curvy thing. This is, of course, an exaggeration. But that's actually not a correct picture. A correct picture is you throw the ball here, the ball goes up. By the time you look at the ball again, you're over here, and the ball is still moving this way, so the ball appears to be to your right. This is not because a force is acting on the ball. It's because the ball is moving outward, and when you move outward, you end up with this weird effect where it looks like you're lagging behind. Coriolis force, fictitious force. Nothing causes it to bend backwards. You're rotating, so it looks like it's going backwards. Okay, this is the most important part of the video, I think, because it kind of brings everything together. So we've got this piece figured out, and notice I got rid of my circle, and all I did now was I just made a curvy line. This is general motion in 2 dimensions. Earlier in the video, I made a velocity vector and I was like, look, it's in 2 dimensions. If you just go straight, this is not really 2-dimensional motion. This is 1-dimensional motion in a weird dimension, right? In one strange direction. In order to move in 2 dimensions, you really need to curve. And when you are curving, I'm telling you that for that part of the curve, you are moving in a circle. Maybe you're moving in different circles at different times, but hey, that's what we've been doing this whole video, changing the circles we've been moving in. So any kind of 2D motion is explainable by the same tools we use to explain circular motion. Let's take a look at what that means. What that means is that if I pick some random part on this trajectory, it has a certain distance from the origin. It has a certain angle it makes. What does the velocity there look like? Well, it's tangent to the trajectory, so it looks something like that. Our normal course of action is to break things into parallel and perpendicular components. But instead of breaking them into XY components, I break it into a piece that's parallel to the radius, and I break it into a piece that is perpendicular to the radius. If you want to know, like, what's the direction of the circle, this is kind of the circular part, and this is the part that's moving outward from it. Each one of these pieces has the accelerations that we talked about before. This piece has the centripetal acceleration. It also has these accelerations as well in order to push them forward. This piece has these accelerations. In other words, all the hard work that we did in order to figure out circular motion has actually paid off, because these terms are present whether you're moving in a circle or not. The most complicated motion can be decomposed into parallel and perpendicular pieces, just like it can for something as simple as ballistic motion. Okay? Hopefully this video was more helpful than confusing.